All right, good morning everybody. So, kumusta ang pagbabakasyon? It's been a while since we met in the lecture. Dalawang linggo, ano? So, kumusta? Nakapagpahinga ba kayo? Or lunod pa rin sa ACADS? Mukhang lunod pa rin sa ACADS, no? Yeah, but I hope you at least found a couple of days to relax, enjoy time with your family and friends, okay? Kaya lang parang wala ng pandemic sa Pilipinas, ano? Aside from everybody wearing masks, I think that's it. Um, Talaga Charles, rest cannot be found. Pasaway kasi yung teacher niyo sa 175 eh, no? Walang patawad. Holy Monday may exer, tapos may exer na naman. Or may nadagdag na exer for last time. Sige, medyo babawi na lang ako sa Monday. Iiklian ko na lang yung lab exer. Because even I was stressed making the answer key for lab exer 3.1 nung Monday. Actually, tapos ko nang gawin yung answer key, but I cannot bring myself to grade the actual papers because bakit nga ba ayoko mag-grade? Kasi hindi pa ako kumbinsido or hindi pa ako sure dun sa final answers because remember the problem there is we need to do the computations for the Gaussian elimination routines using a floating point representation, right? I defined there what the floating point representation or the floating point numeration system should be. Pero ang hirap niyang i-implement sa Excel kasi 'di ba dapat every steps ay 8 decimal digits lang yung na preserve. And it's not just 8 decimal digits the way Excel knew it. Kasi si Excel, ang alam niya na 8 decimal digits, bibilangin niya yung 8 decimal digits after nung decimal point. Tama? Pero the floating point representation requires 8 significant digits. All right? So, medyo merong ibang distinctions doon. So maybe I can share with you something when I upload the answer key for that. Okay. Hindi ko lang talaga ma-discuss sa immediate lectures because I don't want to spoil it for those who had difficulties meeting the deadline due to one reason or another. Tapos pag nag-discuss ako sa lecture and then it will be out in the recording, it will be unfair for those who submitted on time kasi baka makakuha ng hint yung mga hindi pa nakapagpasa. So I think that's one of the problems I have with this setup. Um, Gusto kong i-discuss sana yung immediate exercise right dun sa susunod na lecture session. Pero ayokong ma-spoil yung lab excerpt for those who haven't submitted, which will be unfair for those who submitted early. So, so pagpasensya nyo na medyo hinahanap ko pa rin yung right balance. So I'll try to make maybe a short recording about it and send to everyone who already submitted the uh, uh, the lab excerpt for or probably via email na lang later this week. And then meron akong ilang problema dun sa lab excerpt 2.2. My numbers don't match exact the majority ng mga nasa D2L. Um, Siguro one thing that I can one thing that I think happened ay dun sa computations ng lambda sub n na ginamit dun sa I, right? So there are several conventions na kung paano ko computein yung lambda sub n, di ba? Dun sa computation ng I, kailangan nyo ng values ni lambda sub n. And usually the computations for lambda sub n will depend from method to method. Yung nasa module number 6, module number 5, siya ay yung computations ng lambda sub n para sa fixed point iteration at para sa regular fallacy. So if you're using the Newton-Raphson method, there's a different way for computing lambda n. Pero mayroon lang yung very slight difference. And you can say that that difference is negligible kasi yung lambda n ng Newton-Raphson, mag-approach yon sa asymptotic error constant. Eh, pagka ginamit niyo yung formula na nandun sa module 5 na para sa regular fallacy at para sa fixed point iterations, yung lambda sub n nyo ay magkakaiba lamang ng isang term. So dun sa tunay na lambda sub n sa Newton-Raphson, parang mababawasan lang ng isa or ma-adjust lang ng isa yung subscript. So yung lambda sub 6 using the formula for fixed point iteration or regula falsi in module number 5, yon yung magiging lambda sub 5 doon sa Newton-Raphson. So medyo may mga subtle differences, pero in the long run they will all converge to the asymptotic error constant. So it doesn't matter too much, pero magkakaiba ng konti yung mga numbers na makukuha natin. So kaya nilagyan ko ng question mark yung ibang sagot sa D2L na how did you get this value? Because though theoretically it doesn't make too much difference kung ang ginamit yung lambda sub n ay yung nandun sa module 5. But I want to see na at least i-define nyo kung paano nyo kinompute yung lambda n dun sa mismong exercise. So I can recreate your solution. All right. I won't look for any explanation if the lambda n that you used is what is given in the class or what's the appropriate convention for lambda n that was defined for the Newton-Raphson method. Pero kapag merong subtle difference dun sa values ko nakuha, nagbigay lang ako ng I think 1 point deduction, all right? Pero pag inexplain nyo na, sir, ganito ko po kinompute yung lambda sub n dun sa mismong file nyo, then I gave perfect credit for that. Okay? So I hope that's fine. Sa D2L, ganun yung ginawa ko. Hopefully, ganun din yung gawin ng lab instructors on the from the other lab classes. And then I'll add i-upload ko rin yung answer key para doon sa 2.2 later in the week. Meron lang ako idadagdag na isa pang posibleng solution. All right? Okay, so I think that's it. Any questions? By the way, I think I graded all of the problem sets that were submitted via Canvas. So, paki-check na lang. Hindi pa ako makapaglabas ng top-notchers kasi hindi ko pa na-checkan yung mga nag-submit via email. I'll try to do that within the week. Ang hirap bumalik galing sa 2 linggong bakasyon, no? So, medyo nag-adjust pa. May hangover ng vacation. Yes, CK, may tanong ka?
Hello po, sir. Rinig po ba?
Yep.
Regarding po, sir, sa problem set 1.2, pwede na po ba magtanong doon?
Lahat ba kayo nakapagpasa na ng siguro later na lang, CK, pagpatapos na yung class kasi naka-record na kasi tayo. Tapos meron pa ring isa or dalawa na hindi pa nakapagpasa ng problem set. So either sasagutin ko yung question mo, i-discuss ko yung solution, tapos papalitan ko yung tanong para sa kanila, or sasagutin ko na lang mamaya pag off na yung recording. Tapos para hindi ko kailangan palitan yung problem para sa kanila kasi baka nasimulan na nila yung pagsasagot dun sa PS1 problem set 1. Okay? Okay lang ba 'yan?
Yes po, sir. Salamat po.
All right. Okay, so let me start the recording now. Sorry, not the recording, my screen sharing again. Oops. Sala. By the way, kaka-upload ko lang nung module number 7. Siguro kanina mga 4 a.m. Actually, number 7. Kasi simulan ko siyang gawin sa latex kailan? Nung Monday, all right? Tapos hindi ko talaga maisip pa kung paano ko ikukwento or ano yung i-discuss ko actually sa module 7. So I need to procrastinate a little bit. Tapos kagabi naisip ko ay masyadong mahaba pala, marami pa ring matrices na involved. So ginawa ko, sinulat ko na lang siya muna. So ganun yung nangyari sa module number 7. May 2 pages na typewritten, tapos yung sumunod na ay handwritten na. So if I find time later this week, I'll latex this so mas madali niyo siyang mabasa. But I hope you can read my handwriting right now. Ito pala, dapat nag-hire pala ako ng SA, no, para taga-latex ng modules. But anyway, okay. But before we go there, I wanna I want to say something about Gaussian elimination, and I added this as the last page in module number 6. So if you don't have this page yet, re-download or actually download the latest version of module number 6. Okay, now you might be wondering, why the focus on Gaussian elimination? There are some easier ways on how to solve a system of equation. All right. So halimbawa, a system of equations. Halimbawa, um, yung paggamit ng inverse ni A. So essentially, if you have a matrix system, um, if you have a matrix system A, or sorry, if you have a linear system in matrix form AX equals B, and you know that A is non-singular, okay? So ibig sabihin, nag-exist yung A inverse. So an easy solution to the system, at least theoretically, would be to multiply both sides or left multiplication by A inverse. Hello? Naputol ba ako? Sorry guys, nagloloko yata ang internet ko. But anyway, what we can do is to multiply both sides by A inverse to the left, because again, you need to be careful about matrix multiplication because it's not commutative. So if you multiply A inverse to the left, sa kaliwa, sa left din kayo magmumultiply ng right-hand side ng equation. So, of course, you have to check several things. Dapat proper yung dimensions, but that's fine here. A is a square matrix. It's n by n. Tapos si B ay n by 1. All right. So this guy, the inverse of a square matrix is another square matrix. So this is still n by n. B is n by 1. Tapos yung middle dimensions dapat nag-agree. That's the only time that matrix multiplication will make sense. So in this case, it's fine because this would be an n by 1 matrix, all right? So tapos ang property, A inverse times A is the identity matrix of the right dimension times X equals A inverse B. And it's called the identity matrix for the reason that when you multiply it to any vector or any matrix, it will retain the identity of that matrix multiplier. So ibig sabihin ng I sub n times X will just be X. So the solution is actually A inverse B. So when you're looking at it from a theoretical point of view, it seems very easy and much easier than Gaussian elimination. Kasi A inverse times B, no need for elementary row operations, no need for back substitution. But the problem here is really actually computing A inverse, because A inverse is another matrix on its own. And actually computing A inverse is much expensive than Gaussian elimination. I made a note here that if you will count the number of arithmetical operations, meaning how many additions and multiplications should be carried out in order to find the inverse of the matrix A of dimension n, kailangan mag-perform tayo ng, I think it's 2n cube. Yeah, there we go. We need 2n cube arithmetical operations. So imagine if you have a 100 by 100 coefficient matrix, computing A inverse would be 2 times 100 cubed operations ang kailangan. So medyo malaki yung kailangan mong computational budget para makompute si A inverse. And not just that, computing A inverse is very unstable. So mahirap mag-compute generally ng inverse. Kaya kahit si MATLAB, yung default niya pagsasolve ng matrix inverse kasi ng pagsasolve ng system ng isang equation, meron kasi siyang intrinsic or built-in capability to do that. Okay. So yung pagko-compute niya ng inverse or pagsasolve niya ng system ng equations ay ina-avoid niya by design yung pagko-compute ng A inverse. So gumagamit siya ng konsepto ng pseudo inverse, which I hope to tackle maybe 2 weeks from now. Okay? So kaya talagang hanggang kaya ina-avoid natin yung machine implementation ng A inverse. That's why it's a no for us in using the actual inverse of a matrix because it's very costly. All right. Meanwhile, Gaussian elimination without pivoting will only require 2n cubed plus 3 halves n squared minus 7/6 n operations. So although both of them are order big O of n cubed, all right, medyo kakaunti. Mas maliit ng konti yung budget na kailangan mo para sa Gaussian elimination. Kasi in the long run, yung Gaussian elimination, you can think of it as 2/3 of n cube, yung number of operations involved. Because when n becomes large, this lower order terms doesn't matter too much. So pwede mong tingnan roughly 2/3 ng n cube yung complexity ng Gaussian elimination without pivoting. Tapos yung mga pivoting strategies at every pass, nadadagdagan lamang naman ng isang nadadagdagan ng row interchange. So yung mga may pivoting strategies, hindi rin ganun kalaki yung number of operations. I think it will still be around 2/3 of n cube in the long run. Okay? Pero yung inversion, matrix inversion will require 2 n cube operations. So mas makakatipid tayo sa Gaussian elimination. And actually, Gaussian elimination is more numerically stable than matrix inversion. Tapos yung mga nagwa 120 dyan or Math 120 or AMAT 105, probably you have heard of the reduced row echelon form. Okay? Now, mas malaki ng konti yung computational budget na kailangan para sa reduced row echelon form, reduction ng isang matrix. Yun yung tinatawag nating Gauss-Jordan elimination. Hindi ko na siya itatakal dito kasi from a computation standpoint, Gaussian elimination is much more superior than Gauss-Jordan. Kasi yung Gauss-Jordan, n cubed plus n squared minus n arithmetical operations yung kailangan. And I think anyway, you will see this process in your linear algebra course. So yun dahilan kung bakit medyo nagpo-focus tayo sa Gaussian elimination, right? So we'll try to build up on that and go to module 7. Okay. Now, medyo kailangan kong baguhin yung preface ng module 7 because depending on what we'll finish today, baka LU factorization lang yung ma-discuss natin today. I promised here in the module that I will also talk about non-LU matrix factorizations in the week. Pero mukhang hindi ko siya kakayanin kasi nung nagsusulat ako kanina, nagduda na ako kung matatapos ko yung LU decomposition in just one meeting, which is today. So I promise here Cholesky and QR factorization, but I'm not sure if you'll be able to tackle it. So I'll make the proper adjustments. Swerte kayo kapag hindi na yung Cholesky at saka yung QR decomposition kasi mas maiksi yung nyo for Monday. Okay. Oh, sabi ni Michael, hindi pa nakikita yung module 7. Hold on. Thank you, Michael, for calling my attention on that. Teka. Buti nakalagi na ako kay Canvas ngayon. Okay. Yeah, same problem. Thank you, Michael. Hindi pa nga siya available. Nakalimutan ko siyang i-publish. Now, it should be there. Okay, so live na siya kay Canvas. So essentially, for this week, or at least for this session, we'll do an LU decomposition of a given matrix, and then you will see that this is very much related to Gauss-Jordan elimination. Sorry, not the Gauss-Jordan, but the Gaussian elimination that we discussed last week. All right. Now, ano yung idea behind matrix factorizations in general? So remember pag nag-solve tayo ng polynomial, halimbawa polynomial equation x squared minus 9 equals 0. Okay? So halimbawa yun yung sinosolve natin. Now, the thing that we do is we rely to the zero multiplication, the zero product property ng mga real numbers. What we do is to factor the polynomial on the left. So gagawin ko yung x plus 3 times x minus 3 equals 0. And then using the zero product property, we'll get the solutions we'll get the two equations. Sorry, there should be an or. X minus 3 equals 0, which will imply that either x is equal to 3 or negative 3. So yan yung factorization natin sa polynomials at paano natin siya ginagamit sa pagsasolve ng mga polynomial equations. Now, there's an analog to it pagdating sa matrices. And that's what we'll be looking at today. So ang isang matrix A, pwede nating i-decompose into two matrices or into the product of two matrices. C times D for almost all matrices. All right? Actually, pwede pala nating i-factor lahat trivially, lahat ng mga matrices kahit singular yan or non-singular kasi pwedeng isulat mo si A as A times identity, all right? So that's a factorization but a trivial one for the matrix A. But the idea is, baka naman may analog yung factorization sa pagko-compute ng solution sa isang linear system. And that's what we will look at today. Pero ang problema, ang matrix factorization is not unique. So ano ba sa linear algebra ang tawag natin? Hindi siya isang unique factor. Ang set of all matrices ay hindi isang unique factorization domain. Meaning pag meron ka isang matrix A, posibleng marami siyang factorization na involved. So hindi katulad ng polynomials o hindi katulad ng mga numbers na meron silang unique non-trivial factorization. So sa matrices, there could be several ways on how to factor a different matrix that doesn't vary trivially or that don't vary trivially. All right? So titingnan natin, pipiliin natin yung mga magandang form ng factorization. So we will put nice structure on the factors C and D of the matrix A so that the system AX equals B is convenient to solve. Okay? So yun yung idea. And then, sir, bakit pa tayo naghahanap ng panibagong solution? Parang maayos na yung Gaussian elimination. Well, that's true. Nakita natin sa module number 6 na parang na-address naman ni Gaussian elimination yung problema ng ng round-off errors o ng machine precision. Because we have seen that if you will just put pivoting strategies into your system, even if you're doing it in a low precision machine, you will get fairly accurate results. Of course, that is bounded above by the machine epsilon, but that's fine. Okay. Pero nagulantang tayo dun sa LabXer 3.1. Hopefully nagulantang kayo. Nakita nyo parang hindi nagme-make sense yung solution ko sa LabXer 3.1 kasi bakit i-spoil ko ba? Wag na lang. Baka meron pang hindi nakapagpasa ng Xer. Pero I hope you know what happened there, right? So parang pinagdudahan mo, tama ba tong ginawa ko? Bakit ganito yung result? Bakit mas maganda yung result from this method from the other method even if hindi siya katulad nung even if yun yung promise na nandun sa module 6 na etong method na to will address the issues that would have come from Gaussian elimination without pivoting plus computer implementation. All right? Tapos magtataka pa kayo, bakit nga ganun yung nangyari? Kasi 8-digit rounding arithmetic yung ginamit namin. So, pero dun sa module, parang ilang digits lang ba yung ginamit natin sa modules. And we have seen significant improvements. So when I upload the answer key to 3.1, I will include a short discussion about that phenomenon that we have seen. Ang ganda nung nangyari kasi sa XR 3.1, we stumbled upon another phenomenon na hindi na-cover nung module number 6. Admittedly hindi siya on purpose, all right? So nagulantang din ako nung ginawa ko yung solution, and then I tried to think what is the possible problem, all right? And then I found out na, okay, kaya pala, kasi ganito yung matrix A. And you kindly read the last portion of the answer key that I will upload para malinawan kayo kung ano yung nangyari. Bakit parang hindi intuitive yung sagot dun sa LabXer 3.1 vis-a-vis the promises of module number 6. Okay? Now, going back, so ano nga yung tanong ko kanina? Ang dami kong segue. Ang tanong ko kanina ay bakit pa tayo hanap ng ibang methods aside from Gaussian elimination? Well, it's okay. Gaussian elimination, it's order big O of n cubed number of operations used. There are some ways to mitigate the effects of loss of significant digits from the machine implementation of Gaussian elimination, and that is by using the pivoting strategies. So why look for other methods? Isn't the Gaussian elimination foolproof, right? So it is not foolproof as you have seen in Lab Exer 3.1, even if we have addressed the issue of loss of significant digits. Pero may isa pa siyang problema. Malaki pa rin masyado yung order n cube or yung order big O ng 2/3 n cube na number of arithmetical operations, especially if solving the linear system is just a little part of a bigger code, right? So halimbawa, meron kang mahabang program, tapos meron siyang isang section na kailangan mag-solve ng linear systems ng paulit-ulit. So yung big O of n cube number of operations is very expensive if you have to run it thousands of times or thousands of iterations. And another thing is, hindi na siya nagiging computationally efficient, especially if you want to solve a bunch of equations of the form AX equals BK. Okay. Halimbawa, meron kang mga system of linear equations na pare-parehas yung coefficient matrix A, pero posibleng iba-iba yung right-hand side. Okay? So ano yung mga posibleng remedy dito sa issue na to kung paulit-ulit mong kailangang i-solve yung system pero nagbabago yung right-hand side? Well, kapag alam mo na lahat ng mga B sub case, alright? Alam mo na lahat ng posibleng right-hand side, so ang pwede mong gawin, magbuo ka na lamang ng isang mas malaking augmented matrix. So meron kang B1, B2, B3, until B sub K. Alright? So instead of isa lamang yung ino-augment mo na column, i-augment mo na lahat ng mga B sub Ks. Tapos, di pala to B sub K. Gawin natin B sub M. Alright? Kasi K yung generic subscript ko. Tapos, pagka na-reduce mo na to sa upper triangular matrix, then D1, D2, D3, hanggang DM, alright? Gagawin mo na ngayon yung back substitution pa isa-isa. So, magba-back substitution ka na sa UD1, magba-back substitution ka ng UD2, back substitution ng UD3, and so on. Okay? Pero once ka lang, nag-Gaussian elimination. Alright? Magpe-perform ka lang ng M separate back substitutions to complete the solutions for all of the systems of equations. But this remedy will only work if you know all of the BKs beforehand. Malalaking mga routines kung saan required ka na mag-solve ng mga system of linear equations ng paulit-ulit, alright? Yung mga B sub case, hindi sila posibleng given na kagad from the onset. The right-hand side vectors might be results of an iterative process. Posibleng yung proseso pala ay mag-start ka sa isang B sub 0, tapos mag-run ka ng algorithm, tapos magkakaroon ka ng system AX equals B sub 0, tapos posible na yung solution na to, siya yung magiging B1. So, ibig sabihin, hindi natin mape-perform yung bigger augmentation na dinescribe ko kanina kasi hindi pa natin alam lahat ng mga B sub i's from the get-go. Alright? So that means posible na, okay, susunod pa ay AX equals B1. Tapos yung solution na to, parang fixed point I, ano? So yung solution dito sa system na to, posibleng siya yung kailangan mong B2. Tapos siya uli yung ipapasa mo dun sa susunod na system. And so on. So this is a very tedious process, especially if kailangan mo itong gawin ng paulit-ulit. So napaka-computationally expensive na nung total program mo. Kasi bawat isang solving nito ay big of n cube operations yung kailangan. Right? So kung ang isang run ng program or isang run nito will take you a couple of minutes, tapos meron kang 1,000 systems na kailangang i-solve, so baka hindi ka makagraduate sa isang SEM. Alright? Hindi mo matapos yung thesis mo kasi ang tagal nung implementation. Alright? So that's the motivation for factorization methods. Alright? Because we will develop some techniques here on modifying the matrix A so that we can develop an easier way of solving systems even if we don't know the right-hand sides. Para ang gusto kasi ditong mangyari, maging katulad siya nung case na lahat ng B sub case ay determined from the start. Wherein I can just do the back substitution whenever the right-hand side vectors become available without the need para dun sa further manipulation ng matrix A. or without any other pass of Gaussian elimination. All right? So yun yung idea na gusto kong gawin today. And apparently, Gaussian elimination gives us one nice way for factoring the coefficient matrix A. And that's what we want to do today, which is what we call LU factorization. Okay? Ano yung LU factorization? The LU factorization of a matrix A is the decomposition of the matrix A into the product of a lower triangular matrix L times an upper triangular matrix U. Right? So ito yung hinahanap natin na factorization para sa isang matrix A. Right? Product siya dapat, nasa kaliwa yung lower triangular, nasa kanan yung upper triangular. And you need to be very careful with ordering the multiplications here because again, I hope you already seen that matrix multiplication is not commutative. So yung LU ay iba siya sa UL. Alright? So kaya kailangan LU talaga to, lower times upper triangular. And when we say lower triangular, ito yung mga matrix na ang mga non-zero entries lamang ay nasa ilalim ng main diagonal. I think last time na-define lang natin yung upper triangular. To complete our exposition, yung lower triangular matrix, ganito naman yung itsura. So ito yung main diagonal. Right? The main diagonals or the main diagonal can contain any real number. Tapos, nasa ibabaw, nung lahat ng entries sa ibabaw or sa taas ng main diagonal ay puro zeros. Yun yung tinatawag natin na lower triangular matrix. Alright? So, how can we realize an LU factorization for a matrix A? Well, as I mentioned, Gaussian elimination will lend us an algorithm on how to find an LU factorization kasi ano nga ba yung nangyayari sa Gaussian elimination? Nare-reduce natin yung coefficient matrix into an upper triangular matrix. And apparently, that upper triangular matrix can serve as the U in the LU factorization, and we just need to keep our fingers crossed na yung multiplier na makukuha natin supposedly out of the Gaussian elimination ay isang lower triangular matrix. Okay? But in order for us to do that, we need to look at Gaussian elimination in a more matrix-friendly, or hindi pala matrix-friendly, how do you say it? Maybe I'll say a more algebraically friendly perspective, all right? Kasi parang napaka-artificial ng elementary row operations kasi description yung binigay natin sa kanya. Number one, interchange of rows, right? Parang ano lang siya, parang wala siyang ka-algebra na alam niyo yun. Parang wala siyang algebraic flavor to it. Kasi parang arbitrarily pagpapalitin mo yung rows ng isang matrix. Tapos magmo-multiply ka ng isang non-zero scalar sa isang row lamang. Right? It doesn't make sense because ang alam lang natin ng operations sa matrices ay addition at saka multiplication, possibly inversion, transposition, pero parang hindi algebraically nagme-make sense yung elementary row operations. Well, if you will just look at those operations from the context of Module 6, then you might be right. But apparently, elementary row operations actually has the same action as pre-multiplication by what we call elementary matrices. So yung mga nangyayari pala dun sa Gaussian elimination ng mga elementary row operations, hindi lang pala sila random operations. Yun ay resulta ng pre-multiplication or left multiplication by some special matrices. Ang tawag natin sa mga special matrices that can mimic the elementary row operations ay mga elementary matrices. And that's what definition 6.1 is about. Eto na, tapos na yung pagpapanggap ng Module 7, handwritten na yung uli yung natitira. Okay. Ano yung mga elementary matrices? Now, we say that the matrix E, a square matrix E, is an elementary matrix if and only if it is the result of applying an elementary row operation dun sa identity matrix. Right? So, pagka si identity matrix, pinagpalit mo yung dalawa niyang rows to get the matrix E, ang tawag natin kay E ay isang permutation matrix because you are changing the ordering of the rows. Kaya siya permutation matrix. Okay? Now, if you replace a row by a scalar multiple of that row, remember ito yung pangalawang elementary row operation, okay? For some non-zero scalar, then the resulting matrix E ay isang elementary matrix tapos tawagin natin siyang row scaling matrix. Kasi parang binago mo lang by a scalar multiple yung isang row. Inimbento ko lang tong title na to para lang meron tayong magandang tawag, maiksing tawag doon sa elementary matrix that can scale one of the rows of the given matrix. All right? So pag meron kang identity matrix, minultiply mo ng isang non-zero constant yung isang row niya, identity matrix, minultiply mo yung isang row niya by a non-zero constant, then what you get is a row scaling matrix, which is elementary. Okay? Tapos, yung pangatlo, ito yung result ng type 3 elementary row operation. When you replace a row of the identity matrix by that row plus a scalar multiple of another row, then what you get is what we will call as a row translator. At yung row translator na yon ay isa ring elementary matrix. So sa bawat isang elementary row operation, tatlo di ba yung define natin sa module 6, alright? Meron tayong elementary matrices that correspond to them. Now, tinawag silang or parehas silang tinawag na elementary. Magkamukha yung title nila, not just because elementary matrices are products of elementary row operations on the identity matrix, but because elementary matrices have the same action to any other matrix. Wala ako sa sentence, sorry. I had to sip my coffee. Mali yung English ko. Okay. Hindi lang siya pinangalan ng elementary kasi parehas yung definition. Alright? So, it is elementary matrices have the same action on any matrix as the elementary row operations. And that is through left multiplication. Okay? So, ibig sabihin, kung gusto mong ma-achieve as ayan, sorry, naputol ako. You perform it how we in this manner in how we did it in module number 6, or you can do it as a pre-multiplication of the corresponding elementary matrix. Okay? Halimbawa, okay, balik example 7.1. So actually I was going ahead of myself here. Nag-example pala muna ako ng hindi, tama pala. Pinagsabay ko na nga pala sila sa example 7.1. So, itong matrix na to, by inspection, you can say that this is an elementary matrix. Why? Because it is the product of interchanging row 1 and row 3 of the identity matrix. So, papasok siya as a permutation matrix. All right? So, it's elementary. And again, since this is derived from interchanging the first and the third rows of the identity matrix, then pre-multiplying it or left multiplying it to any other matrix will interchange the first and the third row of that matrix. Kasi parang ito yung pampalit dun sa elementary row operation. And this is much more natural from a linear theoretic point of view, all right, or a linear algebra point of view, kasi well-defined yung multiplication as an algebraic operation. So so you can verify that indeed E times A, where E is this permutation matrix, will give me this guy coming from the matrix A. Ang naging effect niya lang talaga, yung first row ni matrix A napunta sa third row, tapos yung third row napunta kay first row. And this is expected because the permutation matrix is the identity matrix only that the first and the third rows were interchanged. Okay. And then may isa pa, example 7.2. Example 7.2, we have the matrix F. I think kumusta ba guys? Naglalag ba ako? Nag-stop na yung, naghang na yung, naghang na yung screen ko sa laptop. Pero, nasa
Naririnig pa naman namin kayo, sir. Tuloy-tuloy po.
point 2 na ba yung screen ko?
Ayun, naglag na po.
Alright, thank you.
Ayun,
Kainis. But anyway, yung na ba? Or 7.1 pa rin? Ayan, nakita ko na. Nag 7.2 na siya. Alright. So, si matrix F, elementary matrix din yan. Kasi kamukha siya ng identity matrix except that the second row is multiplied by -1. Alright? So basically, it is the 4x4 identity matrix wherein the second row is replaced by negative of the second row or by -1 times the second row. Okay? So basically, kapag nag-pre-multiply ako ng matrix F sa kahit na anong matrix, it will have the same effect. That is, it will just replace the second matrix of the second row of whatever matrix I multiply to it, all right, by -1 times that second row. Okay? So ibig sabihin, pagka kinuha ko yung F times the matrix A defined in equation 7.1, all right, yung FA, yung product na FA will just be as if I perform this elementary row operation on the matrix A. Mapapalitan lamang yung second row ni A by the negative of its second row. Okay? So, mangyayari lamang, pag kinuha niyo yung product na FA, magiging ito lamang siya. Okay? Mamumultiply lamang yung second row by -1s. Okay? So, does it make sense yung elementary matrices? Sabi na nga ba, hindi ko matatapos tong module 7 today. Okay, I hope it's okay. Then sa example 7.3 naman, okay, can you guess ano yung epekto ng E1, ng elementary matrix na E1? Kapag kinuha ko ano yung mangyayari sa E1 times A with respect to the matrix A? Or can you explain why this is an elementary matrix? Or baka hindi naman pala siya elementary matrix, ano? Anyone? Hindi ba hindi ba obvious or apparent kung bakit ito isang elementary matrix? Ano yung ginawa ko sa identity matrix para makuha si E1? Yes, very good, Michael. Yes, nag-row translate ako. You translated the second row of the identity matrix by -33/4 times the first row. Okay? So ano siya? Identity matrix na yung second row ay pinalitan ko ng second row minus 33/4 ng row 1. Okay? Kasi ito ay mamumultiply ng -33/4. 0 to originally. So 0 plus -33/4. That will give me -33/4 over here. Tapos 0 times -33/4, that's gonna be 0 plus the original entry 1. So hindi siya mababago. Itong dalawa ay hindi rin mababago. So I think this is the clue that we did a row translation. Okay? Kasi ang usapan, elementary matrix siya kapag isang elementary row operation lamang yung ginawa mo sa identity matrix para makuha yung matrix E1. Okay? So yun pala, siguro kailangan kong dagdagan yung definition ko ng elementary row, ng elementary matrix. Dapat isang elementary row operation lamang yung ipe-perform mo sa identity matrix para makuha yung elementary matrices. Okay, so Michael is right. So this is just translating the second row by negative 33 over 4 times the first row. So basically, it will have the same effect on any matrix after pre-multiplication. So mangyayari, so ito yon, okay, yan yung kinikwento ko kanina. So if I apply it to the matrix A in example 7.1, you can check na pagka pinamultiply mo yung, pag kinary out yung matrix multiplication, E1 times the matrix A will give you this guy. All right? But again, this should be a pre-multiplication. Okay? Now, maybe you're wondering, ano sir yung nangyayari kapag pabaligtad? Ginawa kong 8 times E1. Well, it makes sense to talk about 8 times E1 kasi si A ay n by n, si E1 ay n by n din. So, define yung matrix multiplication. It will give us an n by n matrix back. Pero ano yung mangyayari? Well, magkakaroon ka ng pagbabago dun sa columns. Alright? Columns naman yung mababago. Alright? Pero it will be tantamount to having an elementary column operation performed, pero dapat yung elementary matrix mo ay obtained via elementary column operations. Pero equivalent lang naman yung dalawa, kaya kahit sa linear algebra, and dito sa numerical analysis, we just chose arbitrarily to work with elementary row operations, but it would have been the same thing or a similar thing will happen if we work with elementary column operations exclusively. So I hope I can borrow the next 5 minutes para matapos ko yung paano yung elementary station. Okay, now I think it becomes apparent now kasi sa bawat isang run ng Gaussian elimination, nagpe-perform lang tayo ng mga elementary row operations. Tapos natutunan natin na bawat elementary row operation ay pwede kong isulat as a pre-multiplication by an elementary matrix. So basically, yung ginawa pala nating Gaussian elimination from module number 6 is basically a successive pre-multiplication of elementary matrices. And having a nicely defined algebraic operation representing Gaussian elimination will give us nice linear theoretic manipulation of the entire process itself. Kaya mas marami tayong makukuha theoretical insights mula dito sa representation na to ng Gaussian elimination. Okay? But let's see. Let's complete the picture here by looking at example 7.4. Nilift ko lang sa example 7.4 yung example 6.1 mula dun sa module 6. All right? If you remember there, we considered this coefficient matrix. Okay? Hindi ko na lang sinama yung right-hand side after the augmentation. Pero sa example 6.1 kasi augmented matrix yung ipinasok natin sa Gaussian elimination. Dito I'm just working with the coefficient matrices muna kasi kunwari hindi pa natin alam yung mga right-hand sides. Okay? So ito yung coefficient matrix doon, tapos ito yung Gaussian elimination process. So ito yung mga elementary row operations that were performed to get or to reduce the matrix A into an upper triangular matrix. Ang gagawin ko, isusulat ko to sa isang multiplication process. Okay? So kailangan ko lang gawin, kailangan kong i-translate isa-isa yung mga elementary row operations into pre-multiplications. Okay? So, simula tayo rito. Kailangan ko itong i-translate. From the original matrix A to this matrix over here, it took 3 elementary row operations. So, ibig sabihin, if I will translate it into a multiplication procedure, I'm expected to have pre-multiplication by 3 elementary matrices. One matrix corresponding to one elementary row operation. And the nice thing about this elementary row operations, they are independent. Ibig sabihin kasi yung mga elementary row operations, isang row lamang yung nababago niya at a time. So it doesn't matter which elementary row operation we perform first, after the successive application of these three row operations, and consequently the three elementary matrices later, ito yung makukuha natin. Alright? So let's see how it is done. Okay. Yung unang elementary row operation, R2 being replaced by R2 minus 33 over 4 R1. Nakita na natin that corresponds to the elementary matrix E1 mula dun sa previous example, example 7.3. Tapos remember yung isang, siguro idagdag ko siya dito. Okay. Oops. Okay. So remember dito sa matrix A, dito sa matrix A, yung pangalawang elementary row operation ay R3 translated by negative 1/2 of R1. So ibig sabihin, para makuha yung elementary matrix corresponding to that operation, tatawagin ko siyang E2, kailangan i-perform ko yung kaparehas na elementary row operation kay 4x4 identity para makuha ko si E2. Tapos ganun pa rin dun sa pangatlong elementary row operation. Dun sa pangatlong elementary row operation, ito yung pinagawa ko. So para makuha yung elementary matrix that will give us the same effect as that third elementary row operation, I will perform that elementary row operation to the 4x4 identity matrix to obtain this guy. Tatawagin ko siyang E3. Okay? So basically, what we will have is E3 times E2 times E1 times A will give us the result of the first elimination pass. Okay? Tapos gagawin ko rin to dun sa natitirang ilan pa bang operations. 1, 2, 3. Dun sa natitira pang tatlong operations. So, dahil itong dalawang operations na to ay nagsama sa isang elimination pass, pwede kong i-pre-multiply them to the result of the previous set of elementary row operations in any order. Pwedeng ito yung gawin kong E5, pwedeng ito yung gawin kong, pwedeng ito yung gawin kong E4, pwedeng ito yung E5, or pwedeng baliktad. Ito si E5, ito si E4. Right? Pero mukhang magkakaproblema ako pag inuna ko to, pag inuna ko to kesa dito. So kasi baka magka-jumble-jumble yung mga rows. Ang usapan lang, hindi nagma-matter yung order sa bawat pass. Pero within passes, that might create some issues. So be careful with that. Okay. So essentially, ito si E4, ito si E5. Kindly double check how these two matrices are obtained. Or actually, these three matrices are obtained. Okay. And essentially, what we have is this. Okay. CA was reduced via 6 elementary row operations into an upper triangular matrix U, given in tapos yung elementary row operations na translate into multiplication by this matrices. Okay. Ang promise natin ay masulat siya in an manner. Okay. And that's what we will discuss on Friday. Pero at least now, we know how equation 7.3 was derived, all right? Alam na natin itong mga matrices na to. Ang gagawin natin on Friday ay titingnan paano ko magagamit yung equation 7.3 para makakuha ng isang LU factorization para kay matrix A. Tapos sana matapos natin kung paano ko magagamit yung LU factorization na yon para makapag-solve ng system AX equals B for different right-hand side vectors B without redoing all these calculations over and over again. All right? Kasi yun nga yung promise natin. Problema kapag yung mga right-hand sides ay hindi natin alam from the get-go. And I promise you, LU factorization will give us a nice and efficient way of computing that sequence of linear systems. All right? But for now, siguro you can practice, verify equation 7.3. Pag multiply niyo yung anim na elementary matrix na yan, tapos isulat nyo ano yung itsura nito as a 4 by 4 matrix. So tapos i-observe nyo ano yung itsura nitong product na to. Lower triangular ba yan? Upper triangular ba yan? Or hindi siya neither of those two. Alright? Tapos pag na-compute nyo na to, i-multiply nyo siya kay A and verify na equal talaga yung product kay U. So para ma-convince kayo na tama yung pinagagawa nating translation ng elementary row operation. Okay? And then another thing that you can practice on is try to go back to example equation 6.9 in module number 6. Tapos kunin nyo yung matrix multiplication representation nung Gaussian elimination dun sa coefficient matrix na nandun sa equation 6.9. And then on Friday, we'll carry on the discussion and see how this matrix equation will give us an LU factorization of the matrix A and how how can it be used in order to solve a linear system. Okay? So do you guys have some questions? Parang bilis na tapos ng oras. Parang nag-discuss lang ako ng elementary matrices tapos 3 examples, ubos na kagad yung isang oras. But anyway, do you guys have any questions? I hope the discussion makes sense. Okay, good. So that means mukhang maiksi lang yung lab exer, promise, sa Monday. I will just ask you to do to use an LU factorization of a matrix in order to solve a linear system. And then ibibigay ko by tomorrow yung problem para sa lab exer 3.2 para if ever gusto niyo mag-practice, yun na yung pag-practicean nyo. All right, para two birds in one stone. You try to practice and at the same time you're doing the lab exer now. All right. Okay, so if you don't have any questions, then we'll meet on Friday. Until then, guys, keep safe and yeah, let's see each other on Friday. Okay. End ko lang yung recording, then andito pa ba si CK? You can stay kung may questions kayo about the problem set.